All right, so this is going to be section 4.5, and section 4.5 is titled Related Rates. And for me, when I took calculus at first, this was a really hard concept for me to understand. And related rates problems can get ridiculously hard really quickly. There's 8 problems in this section, 4 of one kind, 4 of another. And I tried to pick what I would consider the easiest related rates problems that there are to follow, and in some sense the easiest computationally. They can get really crazy hard, but I just want to give you the idea of related rates. Related rates. Related rates problems, well, they exist because some things change together. And in this problem right here, we have a pebble being dropped into a calm pond. So we have this lovely pond, and we drop a pebble into it. Initially, there's no ripples in the pond, but once you drop a pebble into a pond, it starts forming ripples. And simultaneously, the ripples, the outer ripple gets bigger, and 2 things are changing at the same time with this circle, or with this outer ripple. Its radius is getting bigger, and its area is getting bigger. The bigger its radius gets, the bigger its area gets. So the change in its radius impacts the change in its area. So its radius and its area are related, and they're both changing, because what happens here is at 1 second, that calm pond, the outer ripple now has a radius of 2 feet. That's what this says. A pebble is dropped into a calm pond, and concentric circles are being formed, and the radius of the outer ripple is increasing at a constant rate of 2 feet per second. And so at 2 seconds, the radius of this is going to be 4 feet. And at 3 seconds, I can't draw this, the radius of the outer circle is going to be 6 feet. So the radius is changing at a rate of 2 feet per second, and each time the radius changes, the area changes, because the area is, based on the size of the pool, of the circle. So the things are changing in unison, so they're related. The bigger the radius gets, the bigger the area gets. And this problem says at 4 seconds, really, which was when the radius is 8 feet, at what rate is the total area of the disturbed water changing? In general, if I've never been shown how to do one of these problems, I wouldn't be able to figure it out by myself, because you have to read through the problem and interpret the information that's given in a way that that it needs to be fit into a calculus problem. So I'm going to try to do that. I'm going to read through the problem, and every time I get to a number, I'm going to try to tell you in calculus what symbolism that number is going to represent, and that'll make the problem, in some sense, followable, but maybe not something you could create by yourself. But we'll do enough problems where eventually I think you can create the work by create the answers yourself. Even if you don't perfectly understand them, that's okay. So as I read through this problem, we have a nice calm pond. We drop a pebble in, and it's going to make circles. And the most outer circle, its radius is changing at a rate of 2 feet per second. It's a change, and change usually in calculus is given some sort of derivative symbol. And this is a change of the radius with respect to time in seconds. And I'm going to say here, the derivative of the radius with respect to the time, or the change in the radius with respect to the time, is 2 feet per second. And that's the first information that's given for problem 2, is that the radius of this outermost circle is changing at 2 feet per second. This is the symbolism that we need for this. dr dt is the calculus way to say that the radius is changing at this rate of 2 feet per second. Done with up to there, now I move on. When the radius is 8 feet, so when just a generic radius is 8 feet, So done up to there. That's the next given. The radius is 8 feet. What rate is the total area of the disturbed water changing? Here's the question. So this is what I'm trying to solve for. I'm trying to solve for the rate that the total area of the disturbed water is changing. And in calculus, the rate that the total area is changing is given by the symbol dA dt, the derivative of the area, or the change in the area. If A stands for the area, with respect to time, this should be a small d. And that's what I'm trying to solve for. When the radius is 8 feet, and when the circles are getting bigger at 2 feet per second, how is the area of this pond changing at that instant? And this is actually not that hard to do. First of all, I have to realize that I need an equation to fit the diagram here. And each one of these are circles, and I'm worried about the area of the circles. So the equation I'm going to need is area equals pi r squared, which is the area formula for the circle. And now, that's not going to be enough to solve this problem, because in this problem, I'm needing to solve for dA dt. Well, I don't have dA dt there, but I can get dA dt by taking the derivative of this equation with respect to t. So I'm going to use implicit differentiation and take a derivative with respect to t. In general, a derivative of a would just be 1, because it's a to the first power. You'd go 1 times a, you get 1a to the 0 power. It's just 1. And that's if I was taking a derivative with respect to a. But because I'm taking the derivative with respect to t, I'm going to tack on a dA dt. And that's what we did in the last section, implicit differentiation. On the right side, I'm going to do the derivative of the right side. I'm going to bring the exponent out front, make a 2 pi, lower the exponent by 1 to r to the first. If I was taking a derivative with respect to r, I would be done with the right side, but I'm taking a derivative with respect to t. So because I took the derivative of r with respect to t, I have to tack on the fact that I did that. I tack on a dr dt. So really what I have on the left side is dA dt. That's what I'm trying to solve for, because I don't need the 1 there. Is 2 pi r, don't need the exponent of 1, times dr dt. This is nice because now I can take the givens, plug them into the right side, and I'll be able to solve for dA dt. So dA dt equals 2 pi, r is 8 feet, and dr dt is 2 feet per second, 2 feet per second. Just going to multiply everything. I'm going to multiply 2 times 8 is 16 times 2 is 32, and get a 32. Leave the pi, and the first unit is feet, the second unit is feet per second. The feets are both multipliable. I'm going to get feet squared per second. So the pond, the area is growing. At 32 pi feet squared per second when the radius is 8 feet. And that's the entire problem. I'm done, and this is probably the best answer I could give for problem 2. Problems 1 and 3 are just duplicates of this problem with different numbers. So if you followed my work through this problem, you should be able to do problem 1 and problem 3. If you didn't follow it and you need to see me do it again, problem 4 is the same problem just with different numbers. If you compare my problem 1, your problem 1 and my problem 2, the only difference is instead of 1 foot, I have 2. I had to change it to feet because I forgot to change the foot to feet. And you have a 4 feet where I have an 8 feet. So you should be able to mimic what I did for problem 2 to finish your problem 1. I'm going to now do problem 4. And when I do problem 4, it's not any different. It's not a new kind of problem. There's 2 kinds of problems in this section. The first problems are pebbles dropped into ponds. The only difference in any of the first 4 problems are the numbers. So I'm going to do problem 4 now. And again, if you already can do problem 1 with my problem 2, then you probably can do it just fine. And you probably can do problem 3 just fine as well. But I will flash problem 3 up after I do problem 4, just in case you need a little more push. So problem 4, same concept. We have a pebble dropped into a pond, and the radius is getting bigger every second. So the pond is getting the outside circle of the concentric circles is getting bigger and bigger and bigger, and this is kind of the picture. The first bit of information, the rate at which these circles, the radiuses are getting bigger is 4 feet per second. So the first bit of information that's given is dr dt. The rate that the radius is changing with respect to time is 4 feet per second. Done up to here in the problem, this is my diagram of the pond circles getting bigger and bigger, and they're getting bigger, the radius is getting bigger at 4 feet per second. Moving on, when the radius, nothing with change, just the radius, when the radius is 7 feet, done up to there, at what rate is the area changing? And the rate at the area is changing symbolically is the derivative of the area with respect to time, and that's what I'm solving for. Just exactly the same thing that I solved for in problem 2. So I need an area equation for a circle. Any circle has an area equation of pi r squared. I need to take the derivative of the area equation with respect to time. The derivative of a is 1, but because I'm taking the derivative with respect to t, I tack on a dA dt. The derivative of pi r squared is 2 pi r, but because I took the derivative with respect to t, I have to tack on a dr dt. Now I'm going to plug the givens in. So dA dt is the left side, equals 2 pi times 7 feet times 4 feet per second. I'm going to multiply the 2, the 7, and the 4. 2 times 7 is 14. 14 times 4 is 56. I'm going to leave the pi, and I'm going to multiply the feets. So I get dA dt is 56 pi feet per second squared. So the area is increasing by 56 pi feet squared per second. Done with problem 4. The first 4 problems are the easier 4 problems. The next 4 problems are a little bit harder. I can't draw the picture so well, and they're just harder in general. So give problem 3 a go, and then we'll move on and do 5, 6, 7, and 8, which I said they're just a bit harder. Visually, they're harder to interpret, and algebraically, they're a little bit harder to do. So we have 4 problems left. 2 of them are even, 2 of them are odd. They're all 4 essentially the same problem with different numbers. So if you looked at my problem 6 and your problem 5, you'll see that they're exactly duplicates, except my problem 6 has a 2 where yours has a 10. My problem 6 has a 3 where yours has a 6. So they're the same problem. Similarly, if we moved on and looked at your problem 7 and my problem 8, the only difference in each of the 4 problems that were given between 5, 6, 7, and 8 are just the numbers. The words are exactly the same. So once we have one of these done, it'll be a template for the other 3. And like I said, these are just a little kick up in difficulty in terms of being harder. And they're harder for me to draw. I mean, I can barely draw a circle, so my drawings for problems 1 through 4 really weren't stellar. This is going to be awful in terms of my drawing. So air is being pumped into a spherical balloon, something in the shape of a basketball, just a perfect round sphere as opposed to a typical balloon. It's not a perfect sphere. And air is being pumped into this balloon, and I don't think I can draw a balloon so well. So here's my 3-dimensional basketball. And then it's going to get bigger. As air gets pumped into it, of course, it's going to get bigger and bigger and bigger until I guess eventually it breaks. And at every moment, it's just, the shape of a globe, essentially. And it's getting bigger and bigger and bigger. Well, I have to understand what's given to me, what I'm trying to find, and what formulas I can use. And so I'm going to read through the problem and figure out what's given. The first thing is air is being pumped into a spherical balloon at 2 centimeters cubed per second. That's the volume. Because it's cubed, it can tell me that that's how the volume is changing. And I might leave the units out from this problem and just throw units in my answer. I'm afraid that the work's going to be too hard to follow with the correct units in it. So what this first sentence without the units is telling me is how the volume is being changed. 2 cubic centimeters of air are being pumped into this balloon at every second. So the volume is increasing by 2 cubic centimeters every second. And it's going to be the change in volume with respect to time is 2 centimeters cubed per second. Again, I'm afraid to put the units on there because I think it's going to make it a disaster to follow. So I'm going to leave the units off. That's the first number. And then all of a sudden, it sneaks a question right in. So it's worded a little bit awkwardly, I almost think. Calculate the rate at which the radius of the balloon is changing. What is that? The rate that the radius is changing. That's dr dt. The radius is changing. As the balloon gets bigger, its radius is getting bigger every second. So we're trying to find the rate that the radius of the balloon is changing with respect to time. This is what I'm trying to solve for. I don't know how the radius is changing with respect to time. That's what I'm trying to calculate. And I'm trying to calculate that when the radius of the balloon is 3 centimeters. And again, I'm not putting the centimeters cubed per second in the centimeters, but I could. I'm debating. I almost think that it's not going to be a good thing to have those units in there. So I'm not going to put them in there. Alright, so now I'm trying to solve the problem, figure out how the radius of this balloon is changing with respect to time. And the only thing I know is I know that this is a sphere, and I don't have it memorized, but I looked it up. I know the volume formula for a sphere is 4/3 pi r cubed. That's good because it has the letters I need. It has a V and it has an R, and these are the letters that I need. Of course, I can't use this formula because it doesn't have a dv dt, it doesn't have a dr dt, it has an R. To get the dv dt and the dr dt to appear in this problem, I need to take the derivative of this equation with respect to t. In general, the derivative of v would be 1 if I'm taking a derivative with respect to v, but because I'm taking a derivative with respect to t, I tack on a dv dt. To take the derivative of the right side, I multiply the 3 by the 4/3 pi. I lower the exponent 1 to r squared. If I was taking a derivative with respect to r, I would be done. I would need to tack anything on, but I'm taking the derivative with respect to t, so I have to tack on a dr dt. This is nice. The 3's cancel here, and I get dv dt equals 4 pi r squared times dr dt. At this point, I could do some algebra to solve this equation for dr dt because that's what I need to solve for, or I can plug the numbers in. I like the idea of doing a bit of algebra, so I'm going to divide both sides by 4 pi r squared. So it's a little bit harder than the last problem. Visually it's harder, calculus-wise it's harder. Now, on the left side, when I do that division, I'm going to get dv dt over 4 pi r squared on the left side. And on the right side, these are going to cancel. I'm going to get dr dt. That's beautiful because now I can take the numbers that I have picked out from the problem and plug them in. And for dv dt, I'm going to put in 2. I'm going to leave the 4 pi as 4 pi. And then for r, I'm going to plug 3, and I'm going to square it. So the radius is changing with respect to time, and this is going to be the answer once I simplify it. I'm going to leave the numerator, well, I'm going to cancel the 2 and the 4, I think. I'm going to make the 2 a 1, the 4 a 2, and I'm going to make this 1 over 2 pi times 9 equals dr dt. And that's going to give me dr dt is 1 over 18 pi. That tells me the radius is changing with respect to time at 1 over 18 pi. Now if I wanted to get the units in here, if I want to do the units in the numerator, the units in the numerator were centimeters cubed per second. And in the denominator, the radius was in centimeters. And if I squared it, I'd get centimeters squared. So it's going to be centimeters cubed per second divided by centimeters squared. The cube and the square is going to cancel out and give me centimeters per second. So the units are going to be centimeters per second, and I knew it. The radius of this is changing. The radius is just a linear length, so its units have to be linear units. It's increasing at this many 1/18 pi centimeters per second. So because radius is a length, the unit that I need is just the length without an exponent. If I'm trying to find how the area is changing, then I'm going to get an exponent of 2. So with the problems 1 through 4, my units had a square in it because I was figuring out how the area was changing. In problems 5, 6, 7, and 8, because I'm figuring out how the radius is changing, my units won't have an exponent because the radius is a length and the lengths don't have squares or cubes. So my answer for problem 6 is the radius is changing. It's actually growing at 1/18 pi centimeters per second. That's everything I need for number 6. Theoretically, everything you need for problem 7, and everything I need for problem 8. So I'm going to flash problem 7 and 9 up. 7 and 5 up on the screen, because those are the two that you have to do, and they're both exactly the same. If you could do 5, you could do 7. If you can't do 5, you can't do 7. I'm going to do one more problem, and after I do that one more problem, if you can't do these two now, you should be able to do it, because it's the same exact problem with different numbers. So problem 8's the last problem I'll do in this section. It's the last problem in this section. So we have the same balloon that's a sphere. The volume of this balloon is 4/3 pi r cubed. And air is being pumped into it at 9 cubic centimeters per second. So this tells me that dV dt, the change of the volume with respect to time, is 9 centimeters cubed per second. I'm not going to include the units in my work. It makes it too hard to follow. So I'll just kind of write them here but not ever use them again. Calculate the rate at what the radius of the balloon is changing. This right here, calculate the rate at the radius of the balloon is changing. That's what dr dt is. That's the change of radius with respect to time. This is what I'm trying to find. And then lastly, when the radius is 12 centimeters, when the radius is 12 centimeters. So these are the givens and the unknowns. The volume is changing at 9 cubic centimeters per second. I want to find how the radius is changing when the balloon's up at 12 centimeters. So I'm just going to do the calculus. I'm going to take the volume equation for this sphere and take its derivative with respect to time. So the derivative of v is 1, but I have to tack on a dv dt because I'm taking the derivative with respect to t. On the right side, it's going to be, the derivative is going to be 3 times 4/3 pi. I'm going to lower the exponent by 1. Taking the derivative of r with respect to t, so I tack on that dr dt. The left side comes out to be just dv dt. I don't need that 1. On the right side, the 3's cancel, and I'm left with 4 pi r squared dr dt. I'm trying to solve for dr dt, so I'm going to solve for dr dt. I solve for dr dt by dividing both sides by 4 pi r squared. And when I do that, on the left side, I get dv dt, change in volume with respect to time, over 4 pi r squared equals, on the right side, the junk cancels that I want to cancel, and I get dr dt. Now I'm going to plug the numbers in that I have. dv dt is 9, and r is 12. So on the left side, I plug into this formula. In the numerator, the dv dt turns into 9. In the denominator, the 4 pi stays 4 pi. The r changes to 12. And that's going to be dr dt. That's going to be my answer. I'm going to clean this up a little bit. Just have to simplify this. 12 squared is 144. So this is going to be 9 over 4 pi times 144 equals dr dt. 4 times 144 I can't do, but I can do on my calculator. So I'm going to do 4 times 144 on my calculator and get 576. This gives me 9 over 576 pi equals dr dt. That fraction reduces. Without the pi, I'm going to do 9 divided by 576, and then math, enter, enter. The fraction, not the pi part, reduces to 1 over 64. So this gives me 1 over 64 pi equals dr dt. I'm done, other than I should probably write the answer nicely. And I'm going to say the radius is changing and the radius is in centimeters, so it's changing at that many centimeters, and the time is in seconds, so per second. So my answer to problem 8 is the radius is changing at a rate at 1 over 64 pi centimeters per second, because the units of the radius, its length is in centimeters, and the time units in this problem were in seconds. And that's everything for this section that I'm going to do. So if you haven't got them done yet, try to give problems 5 and 7 a go. They're exactly problems 6 and 8 with different numbers. So really there are only 2 kinds of problems in this section. The pebble and a pond problems, which are problems 1 through 4, and then the air being pumped into something that has the shape of a basketball, which were 5, 6, 7, and 8. And that's all that can make their way onto the test from this section. It would be one of those 2 kinds of problems. I probably wouldn't do both of those kinds.